All right. So in the 2D, back in the 2D world, we concerned ourselves with things that we call critical points. All right. So we just talked about it, but let's just draw a picture. Here's a function f of x, and critical points were defined in two ways. One, it's a place where the slope might be equal to 0 or is equal to 0, or the other way to get a critical point is that the slope doesn't exist at a particular place on the curve. So here are two critical points. There's one here at this value of x, whatever it is, we'll call it x1, because the slope there looks like it's 0. And then over here also, we've got a slope that looks like it's equal to 0. So those are critical points, okay? And we also learned in the 2D world that critical points were possible candidates to be maxes or mins of a function. Now I say candidates because you can always think of the example of y equals x cubed, or some translation of that. Say you have a translation like this. Here's a curve that it has a critical point. There's a point here where the slope's equal to 0, the slope of the tangent equal to 0, but it's not a max or a min. So that's why critical points are only candidates for these things. The absolute value graph is another famous example to bring up, because in the absolute value graph, there's actually no point on this function where the slope's equal to 0. However, at x equals 0, f prime of this thing doesn't exist. So that's also considered to be a critical point. A critical point is a place where the derivative doesn't exist. Okay? So now we're going to make the jump into the 3D world, and we'll start with at least half of this. We're going to try and come up with what's analogous to having a slope of a tangent line equal to 0, but in the 3D world. So I'll attempt to draw a picture here. So here's x, y, z, and let's pretend for a moment that we're looking at this function, z equals x squared plus y squared plus 1. So here's a good exercise, just remembering what that graph looks like. Right? So a good way to do that, to try and remember what a graph looks like, you have all three variables present, is to try and think of the level curves, or the topographical map that would go with this. And we just sort of did this when we talked about the gradient and the directional derivative and all those kinds of things. So let's consider the following. If z equals 0, and you take a look at that equation, you'll notice that there's no x and y that can ever make this equation work out, because x squared plus y squared is at least equal to 0, right? For any value of x and y we pick. And then when we add 1 to that, that means that this thing here is always greater or equal to 1. So z equals 0 has no part of a graph to go with it. Z equals 1 would correspond to the point 0, 0, and that's it. Right? Because if z is equal to 1, then x and y would both have to be 0 in order to make this equation work out. So it has to go through this point, 0, 0, 1. Okay. Now, let's try the same thing. There's the equation again. And let's let z equal 2 now. And if you put 2 in here, the equation that comes back is x squared plus y squared equals 1. Well, that's a circle of radius 1. And it's happening when z is equal to 2. So we end up with this. We end up with this level curve. Looks something like this, like a circle with the z-axis as the center, or a point on the z-axis as the center, and it's got a radius of 1. Okay. I guess the last point I'll do, and then I think we'll be set here. Suppose z is equal to 5. Z is equal to 5. Then we get back the equation 4 equals x squared plus y squared. So that means you have a circle with radius 2 at a height of z equals 5. So we go up to z equals 5. So this was z equals 2, 3, 4, 5 is up here. And then we have a circle of radius 2, something like that maybe. And what you're starting to see is this thing. It's called the paraboloid, is what it is. And it's called the paraboloid because if you look at what it looks like in the yz plane, for example, just the yz plane for a moment, in the yz plane, x would be 0. And if x is 0, you'd have z equals y squared plus 1. Well, that's a parabola. If you let y be 0, you'd have the same story, but you'd be in the xz plane. You'd have z equals x squared plus 1. So you'd be in the xz plane. So you have a parabola. I'll attempt to draw it that might go through like that. So you have parabolas in all these planes. And it turns out if you start slicing through an angled plane that contains the z-axis and is perpendicular to the xy axis, then you'll always slice through and get parabolas as your cross sections when you slice through. If you slice through parallel to the xy axis, then you're going to get these circular cross sections. So this is a paraboloid. Now, if I asked you to think about what the minimum z value of this graph is, you could do it, right? You can say, oh, that minimum z value is right here, right? So now thinking back to the 2D world, let's go back to our pictures. When we had mins and maxes, we expected those points on the graph to be critical points. Okay? So I'm sort of expecting the same thing here. Is this a critical point of the graph? And it is. The only thing that's different, though, is that we can't really define a tangent line at that point. We can say, though, is that there's a tangent plane there at that point such that that tangent plane lies below the surface everywhere except at the point of tangency. That, if you think about it, would mean that it has to be a minimum of the graph. So let's think about that again. If you look at this red tangent plane here, all the points on that tangent plane are below the paraboloid, except for that one point of tangency in the middle where the tangent plane and the paraboloid meet. Okay. So actually, thinking back, we know the equation of a tangent plane, don't we? Right? So let's remind ourselves of that. Z minus Z0 equals f sub x of x0, y0, comma, x minus x0, plus partial derivative with respect to y, evaluated at the point of tangency, times y minus y0. Okay? So, from the looks of it, if I look at this picture, it sure looks like that tangent plane's horizontal. That's what it looks like to me. I'd like to confirm that. So I'm going to do that by applying this, what we know about the equation of a tangent plane, and then also the function itself. So we have x squared plus y squared plus 1 equals f of x comma y. I said equals z, but I can write it this way. And I'm going to build the tangent plane. So here we go. F sub x of x comma y equals. And the partial derivative with respect to x would just be 2x. F sub y of x comma y equals 2y. So y is the variable, x squared goes to 0, and so does 1. All right. Now, the way we've drawn that tangent plane, it looks like it's tangent at the point 0, 0, 1. So let's see if we can figure out what these things are. So we do f sub x of 0, 0. We get 2 times 0, which is 0. So that means the slope in the x direction at this point is 0. That's sort of good. That means we're moving. That means the tangent plane, or at least it's horizontal in the x direction at that one point. Let's consider this. So f sub y of 0, 0 is going to be 2 times 0. And that's also 0. Good. So we're moving. If we move in the y direction, this thing doesn't change altitude. Right? And it turns out that that's enough now. Because if we apply the equation of the tangent plane, we get z minus 1 equals 0 times x minus 0 plus 0 times y minus 0. So then you just get z equals 1. And yes, that is the equation of a plane that's horizontal. Okay? And then we also know, because of the nature of the function, here's the function. Think about this. Z equals x squared plus y squared plus 1. You know that this plane that we just found the equation of is always below this surface I've described. And you know that because x squared plus y squared, the least that could be is 0. Right? So this plane here above would always be below the surface except when x was equal to 0 and y was equal to 0, at which point it would be tangent. They'd meet at one point. Okay? So this is sort of the story about how you justify something to be a max or a min in a 3D world. Okay? So what has to happen first is you need a horizontal tangent plane. That's for sure. Right? Because that's going to mean that you're at the top of a hill or the bottom of a hill. Okay, maybe. Not always, but it could mean that. And then you need to also show that the surface is either completely above that plane or completely below that plane for all the points around where you think the point of tangent is occurring. Okay, so let's just state a little theorem. Ready? So if f of x comma y has a local maximum or minimum value, okay, and the first partial derivatives exist. You could say, I should say first order, just to be careful. First partial derivatives exist at this point, at, we'll say a comma b. That's going to be our point of interest. Then f sub x of a comma b must equal 0, and f sub y of a comma b must equal 0. So let's find some critical points for the following. Consider this example. Suppose if f of x comma y is equal to x to the fourth plus y to the fourth minus 4xy plus 1. And the question is, where are the critical points of this thing? Okay? So to do that, we're going to take both partial derivatives, set them equal to 0, and see if we can solve it. Just don't expect nice things to happen all the time when you do this. Okay. So let's start with f sub x. So if x is our derivative that's going to vary, our function, our variable that's going to vary, we take the derivative with respect to x, and then what do you get? Well, you get 4x cubed for that piece. The derivative of y to the fourth with respect to x would be 0. Okay. The derivative of that thing, if x is the variable, then negative 4 and y are acting like coefficients. So it's minus 4y. And the derivative of 1 is 0. Okay. So we know we want that to equal 0. So we'll write this down. That's supposed to be 0. Let's go get a partial derivative with respect to y now. Okay, some nice symmetry here, right? So you have 4y cubed, and then now negative 4x is acting like the coefficient on y. So it's minus 4x equals 0. Okay. So what you'll notice is that here's where things are not quite as convenient as last year. Usually when you found critical points last year, you took the derivative, the first derivative, you set it equal to 0, you had an equation with one variable, and you were able to solve that. Even if you couldn't solve it, you could graph it or use the solve command or something, using your calculator maybe. Here, you don't have that luxury. What you have is you have two equations with two unknowns, and what you have to do is come up with all the points that would satisfy both of those equations. You could definitely start by doing this. First equation could be x cubed. The first equation basically says it's x cubed equals y. That's basically what it says. And the second one, I'm going to write that it's just y cubed minus x equals 0. So you can definitely substitute here to get started. Okay, I divided both equations through by 4, and then the top one I got y alone. So now if I take this y here and I replace it with the x cubed that it's equal to, this equation becomes x to the, or x cubed cubed, I should say, minus x equals 0, or x to the 9th minus x equals 0. Now that's an equation in one variable. I can solve for all the values of x. And once I solve for all the values of x, I already know that y is equal to x cubed. So I'll be able to get the y values that go with them. So let's do this. Ready? I'm going to factor out an x. So you get x times x to the 8th minus 1 equals 0. And then you end up with x times x to the 4th minus 1 times x to the 4th plus 1. That's a difference of two squares. And then this works again. You get x squared minus 1 times x squared plus 1 times x to the 4th plus 1 equals 0. And for the time being, that's never going to be 0, and that's never going to be 0. So that's not going to be 0. You know this can equal 0. So x equals 0 is at least one component, right? Or it's the x coordinate, I should say, of one of the critical points. And then if this is equal to 0, then you get x equals plus or minus 1. So then you have another critical point that looks like this, and then a third one that looks like this. Right? All right. So then lastly, what y values go with them? Well, we had said earlier that y is equal to x cubed during our process here. So if y equals x cubed, that's 0, that's 1, and that's negative 1. So these are the 3 points that have horizontal tangent planes. Now, the question will be next, how do we make a decision about whether those tangent planes always lie above the surface, always lie below the surface, or like x cubed back in the 2D world where the tangent line's partially above and partially below, right? Because back in the 2D world, we had that problem. Just because the derivative is equal to 0, we didn't have the luxury of saying, oh, it's definitely a max or a min, right? So just think about a 3D analog to that. You could you could literally think of this. You could think of an equation where it's a cubic here in the yz plane, and that would let it span out. Like in other words, I guess we'll put another cubic over here parallel to it. So we have like a, I guess we'll call it like a cubic surface, so to speak. It's like, what would we say here? And x is allowed to span whatever way it wants. So here, there's clearly some horizontal tangent planes, but they're not maxes or mins.